So we've seen absolute value functions before. This is not new. We've graphed these things before. In Unit 2, we looked at absolute value functions, square root functions. We looked at quadratic and linear functions. And we looked at transformations of all those functions. So graphing an absolute function, absolute value function, is not a brand new topic. But just as a quick refresher, remember that an absolute value function is V-shaped. And then because I'm adding and subtracting and multiplying by numbers kind of sprinkled throughout this function, that means that I'm not going to have my parent absolute value function with the corner of my V at the origin, but it's going to be moved somewhere. Since we're adding 1 inside the absolute value bars, that means that we're going to move to the left 1 spot. Subtracting 4 outside of the absolute value bars, that means we're going to move down 4. And then this 2 that we're multiplying by in front is going to affect the slope, if we want to call it, of our side. So this is going to stretch. This is bigger than 1. It's going to stretch our graph by 2. So as I go to graph this, I'm going to start kind of hovering at the origin at 0, 0. And then I'm going to move to the left 1, to the left 1, and then down 4. 1, 2, 3, 4. And that's where my center goes. And then normally for an absolute value graph, we would go up 1 and over 1 for those points along the side. But since we're stretching a factor of 2, that means we're going to go up 2 and over 1. Up 2 and over 1. And then we'll do the same thing on the other side. And there's my V shape. For my absolute value graph. Questions for me so far? Okay. So we've graphed these functions before. The change we're going to see today, what we're going to use these graphs for to start with, is to actually be able to tell us about solutions. So here I have a function, right? F of x equals something. Remember, f of x is just like y. But down here towards the middle of our page, well, we actually have our equations, right? Instead of y here, or f of x, I have my absolute value function, same function, equal to 2, or -2, or -5. So here, this is an equation that we could solve. And that's what we're going to use our graphs for to start today. So here, what I'm looking at in my graph is where is this absolute value function equal to 2? Well, 2 would be here on my graph. That's where y is 2. So I can go ahead and graph that as well. Graph that line at 2. And then if I want to know where these two pieces are equal, right? My 2 that I graphed in green and my absolute value function that's in red. If I want to know where they're equal, I'm going to look for intersections. That's why we're talking about this as part of our systems of equations unit. That's how we started solving systems of equations. We graphed this line, we graphed this line, we looked to see where that intersection was, and that was our solution. Same idea here. I graphed my absolute value, I graphed 2, and I'm looking to see where they intersect. Now, it's a little bit different here because for the system of equations, we had y equals something to do with x, or we had 2x plus 4y equals 7, and then another equation, something like that. But we had both variables in there. Here, we're just looking for x. So when I give my answer, I'm only going to care about x. That's the difference here. X is the only thing in my equation, so x is the only value I'll give. But that idea is the same, that I'm looking for where these two graphs intersect. Does that make sense? Okay. So my solutions here would be x equals, this is -4. That point where I intersect, my x value is -4. And then x equals, over here, this point of intersection, that x value would be 2. So x equals -4 and x equals 2. Questions for me so far? Okay. So same idea for this middle guy. A little bit different problem here. Same absolute value function that we've already graphed. But this time I want to know, when is it equal to -2? So I'm going to go to my coordinate plane. I'm going to find where y is -2. And I'm going to go ahead and graph all the way across that little line on my coordinate plane. And now to find what x is equal to, same idea. I'm going to look at those intersections and I'm going to give the x values. So x equals, this would be -2, right? The x value for that intersection is -2. And then over here, x equals 0. The x value there is 0. With me? Okay. For our last one, again, we have that same absolute value function. And this time I want to know, when is it equal to -5? So I'm going to go to -5 on my y-axis and graph all the way across. What would be my solutions here? There aren't any, right? I have no points of intersection here. This is like in our systems problems when we graphed parallel lines. They didn't have any places where they intersected. So we said that meant there were no solutions to the system. Same idea here, okay? My absolute value graph does not touch -5. So that means we have no solutions here. Okay, good job. So we're treating these absolute value problems kind of like a system of equations. When we were focusing on systems of equations, though, we only looked at lines. Do these lines intersect? Do they not? Are they the same line? But we only focused on lines. Here we're looking at an absolute value and a line. Okay. So really quickly, I want to flip ahead to page 164. And I want to talk for just a second about nonlinear systems of equations. Okay, so I'm flipping to page 164 just for a second. Okay. So here in this example up at the top, it says we have a function f of x and a function g of x. So g of x is absolute value. See that guy graph there. And then f of x is this other graph that's got these sort of two curves to it. This is a rational function. We'll talk about those in algebra 2. I don't think you guys would have had any reason to have seen this before now. But there's a rational function and an absolute value function that I have for my system. Not lines, but it's still multiple functions that I'm considering. So that's still a system of equations. I still can solve it using the graph the same way that we solved our linear systems using the graph. So if I want to know what's the solution to the system, I'm going to look for where those graphs intersect. So my solution would be that intersection point. It doesn't matter that they're goofy functions. I'm still looking for the same thing. I'm taking that same idea and applying it to another type of system. If we hop down the page just a little bit to example 3, I've got another, looks like absolute value function and then maybe an exponential function. Two things that are not lines, but if this is my system of equations, I can find my solutions exactly the same way. I'm looking for those intersection points. So no matter what type of system of equations I have, if I'm looking at the graph, solutions are going to be those intersection points. Okay, same idea. Questions for me on 164? Okay, let's hop back to 156. And now let's take a look at how many solutions we can have for our absolute value function. Okay. So when we had our function equal to 2 and negative 2, how many solutions did we have? 2. So we could potentially have 2 solutions. That's an option. We also had an example where we had no solutions, right? So I could have 0 solutions. That's an option. Are there any other options? Where would I have 1 solution? Yeah, I have this possibility to have exactly 1 solution if I'm intersecting just with that sort of bottom point, that center point of my absolute value graph. So I could also have 1 solution. Very good. Questions for me so far? Okay, let's do a couple more examples with these graphs. So if I take a look at number 1, I'm taking the absolute value of x plus 1 and then minus 2. So I want to graph this absolute value. This plus 1 inside those absolute value bars means I'm going to go to the left 1. And then the minus 2 at the end means I'm going to go down 2. So from the origin, I'm going to go left 1 and down 2. And there's my center. I'm not multiplying by anything in front, so I don't need to change the slope of my sides. I'm just going to go up 1 over 1 to get my side point. So I've graphed the absolute value portion. Now I'm going to graph the thing on the other side of the equal sign. This equals 1, so I'm going to go to where y is 1 and draw my line. My solutions are going to be the x values for those intersection points, the x coordinates. So here, x is negative 4. And then here, x is positive 2. So those are my solutions, negative 4 and positive 2. Questions on number 1? Let's take a look at number 2. I've got my absolute value function over here. Minus 3 in parentheses means we're going to move to the right 3 spots. Plus 4 at the end means we're going to go up 4 units. And then this negative in front, remember, means that we're going to flip this. So instead of looking like a V, it's going to look kind of like a mountaintop. So from 0, 0, I'm going to go right 3, 1, 2, 3, and then up 4, 1, 2, 3, 4. And then to flip this, instead of going up 1 over 1 for my sides, I'm going to go down 1 over 1. There's my absolute value function graph. Now I got to graph that 2. So I'm going to go up to where y is 2. And I graph my line all the way across. So my solutions will be the x coordinates of those intersection points again. So that happens when x is 1 and when x is 5. Questions for me on example 2? Okay, you try 3 and 4. For number 3, my absolute value function, I'm going to move down 4. We're not moving left or right any since there's nothing inside those bars with x. And then this 2 in front means we're going to stretch like we did for that first example. Stretch by 2. So from the origin, I'm going to go down 4, 1, 2, 3, 4, and then up 2 over 1. There's my absolute value graph. And then I'm going to graph the other side of my function here, my equation. And that's at 4. So I'm going to go to where y is 4. And then we follow it all the way across. So x equals -4 and +4. Questions for me on 3? Okay, let's take a look at 4. So for 4, we're going to move to the right 1 and then down 2. And then that negative in front, remember, means that we are going to flip our graph. So from the origin, I'm going right 1, down 2, and then we're going down 1 over 1. For the other side of our equation, I'm going to go to where y is 3. And then again, follow that all the way across. I have no intersections on this one, so what does that mean? No solutions. Good. No solutions. So graphs are a great way to be able to find solutions for absolute value equations, but they're not always going to be as nice as the examples that I've given you here. We very easily could have said, what if I've got this function and x equals 1? Or y, I should say, equals 1. What if I have this equal to 1? That means I've got something here, and I would have to sort of estimate where those points are. Or what if this was equal to a fourth? And now I've got something here, and again, I'm estimating where my points are. And I'm even estimating where I'm putting a fourth on my graph. That can make it a little trickier. If we turn the page to page 158, what we're going to talk about next is how to be able to solve these functions algebraically when the graph is not a good option. So if I take a look at my function at the top of page 158, this is an example of a function where a graph is maybe not the best option. I can find where y is 5, and I know that this minus 3 means I would move to the right 3. But what about this 2? I know what to do with the 2 if it's in front of the absolute value bars, but we don't know that transformation if it's inside. So I don't know what to do with that. You can always graph by making a table, picking some values for x and plugging them in. But that's not going to guarantee you that you're going to get nice values for y. So again, you may have some estimations and some errors in your graph based on having to make estimations. So we're going to talk about how to solve absolute value functions algebraically. The good news is it's pretty similar to how we solve just regular old linear functions. Now, before we talk about solving an absolute value function, I want to do a quick refresher on what an absolute value function is telling you, right? When you take the absolute value of something. So if I were to take the absolute value of 2, what would that give me? 2. Yeah, the absolute value of 2 is 2. What if I take the absolute value of negative 2? That's also 2, right? Absolute value, we can think of as sort of a measure of distance. How far away are you from 0? We don't care necessarily what direction you're going, just how far are you on the number line from 0? It's like if I asked you, how far away from the high school do you live? You would tell me so many miles or so many blocks away. You wouldn't tell me you lived -2 miles away if you lived south of the high school. You wouldn't just say I live 2 miles away. Okay? It's like this measure of distance from our origin, from our center of our graph. Okay? So we need to keep this idea in mind when we talk about solving absolute value functions. So for my function here, the absolute value of 2x minus 3 equals 5, for my equation, I should say. We know that 2x minus 3 could have just equaled 5, like how the absolute value of 2 is 2. So maybe 2x minus 3 just equals 5. But there's another possibility I have to consider. 2x minus 3 could have actually given me -5. And then when I took the absolute value, that's how I got +5, right? Because the absolute value of -2 is still 2. So I have to set up a second little equation here, giving me that possibility. Maybe inside those absolute value bars, I actually got -5, and the absolute value is what made it positive. Okay. So this is kind of the extra step I have when I solve absolute value equations. I have to look at both options. From here, we're going to solve each of these the same way we would solve a regular linear equation. Okay, we're going to get x by itself. So over here on the left, I'm going to start by adding 3 to both sides. So I get 2x equals 8. Then I'll divide both sides by 2 to get x by itself. And we get x to be 4. On the right-hand side of my paper, same idea. I'm going to start by moving 3 to the other side. So I get 2x equals -2. And then divide both sides by 2, and I get x to be -1. When we're solving any type of equation, you can always go back and check your work by taking your solutions and plugging them back into your function. I want to show you what happens when we do that. So if I take 4 and plug it back into this function, I would have the absolute value of 2 times 4 minus 3 equals 5. 2 times 4 is 8. 8 minus 3 is 5. So I would get the absolute value of 5 is 5. And that's true, right? The absolute value of 5 is 5. So that first solution we got works. If I plug in -1, this would look like the absolute value of 2 times -1 minus 3 equals 5. 2 times -1 would be -2. -2 minus 3 would be -5. So I would have the absolute value of -5 is 5. That's also true, and that was that other possibility we had to consider. So maybe that stuff inside the absolute value bars gave me the negative, and it was the absolute value that turned it positive. Questions for me so far? Okay, so we're going to go through a couple more examples solving algebraically. So for A, we've got the absolute value of x over 5 equals 1. So again, we have two options. Maybe x over 5 is equal to 1. But maybe x over 5 is equal to -1. We're going to solve each of these for x. Since I'm dividing by 5 here and I want that to go away, I'm going to use that opposite operation, which would be multiplication. So I'm going to multiply by 5 on both sides. So I get x equals 5. And then for my other little equation, same idea. I'm dividing by 5 and I want it to be gone here. I want just x, so I'm going to multiply both sides by 5. And we get on the other side x equals -5. So there are two solutions, x equals 5 and x equals -5. Questions for me on A? Okay, let's take a look at B. So notice for B, we don't have the absolute value thing by itself. For that first intro example we did, for A, we had the absolute value thing by itself. But for B, there's a -5 in front. I need to get the absolute value piece by itself before I split it up and set it equal to positive and negative. Okay? So our first step here is going to be divide both sides by -5 to get this guy out of here. I want the absolute value thing by itself. So I get the absolute value of 3 plus 4x equals 23. Now that I have the absolute value thing by itself, I can set it equal to positive 23 and -23. So I want you to notice here, we moved anything that wasn't inside the absolute value bars, but if it's inside those bars, we leave it alone. Okay, don't mess with anything inside those until you're setting equal to positive and negative. From here, solve for x. So subtract 3 from both sides. We get 4x equals 20. And then divide both sides by 4. And we get x to be 5. So there's one solution. For my other equation, same steps. Subtract 3 from both sides and we get 4x equals -26. and then divide both sides by 4. And we get x equals, this doesn't come out to a whole number, but I could reduce since these are both even. That would be negative 13 over 2. Or if you wanted negative 6.5, either of those is fine. So there's our other solution. Questions for me on B? Okay, just a couple more here. For C, again, I've got stuff over here on the same side as my absolute value. So I want to get the absolute value thing by itself. That means I've got to move this 3. So we'll subtract that 3 to the other side. So we get negative absolute value of 8x minus 6 equals 0. And then this negative hanging out in front is the same as when we had negative 5 in front. This time it's just negative 1. So I want to divide that off to the other side. So I would get the absolute value of 8x minus 6 equals 0. Now that the absolute value portion is by itself, I can take that and set it equal to 0. And then 8x minus 6 equals negative 0. Do I need to do this? No, 0 isn't positive or negative. So on those couple of problems maybe where you get it equal to 0, you cut to a little break because you only have to do 1. So I want to get x by itself. I'll add 6 to both sides. 8x equals 6. Divide both sides by 8. And we get x to be, this would reduce to 3 over 4. Questions for me on C? Okay, we're going to take a look at one more together for today. For D, we have the absolute value of 1 minus 5x equals negative 4. I just said something really strange. The absolute value of something equals a negative number. Why is that a problem? Yeah, when I take the absolute value, I shouldn't have a negative. Now, we looked at a problem earlier where my absolute value portion equaled something negative, but it was because I was multiplying the absolute value by negative 5. And when I moved it to the other side and had my absolute value piece by itself, it equaled a positive number. Here, I don't have that. The absolute value piece is by itself. There's nothing else over here, okay? I'm not subtracting anything. I'm not multiplying by a negative. I'm saying that this absolute value is 4, negative 4, negative 4. That's not right, right? That's not okay. So what do you think that means for this equation? Yeah, no solution. No solutions there. So I want to point out really quickly that when we looked at our graphs, we said we could have 2 solutions, we could have no solutions, or we could have 1 solution. We saw the same thing here algebraically. We could have 2 solutions, and this guy up here had 2 solutions. We could have no solutions, or I could have 1 solution. Questions for me for today? Okay. Your homework is on the next page, page 159. When I see you on Monday, you guys in person and you guys on Zoom, we're going to do some more examples of solving absolute value equations. And then that's it for Unit 4.